In this video, you're going to see just how little has to go right in order for a USB device to list in some way in Device Manager and in Linux dmesg, and hopefully find something useful to use in your thinking when troubleshooting USB problems. Recently, I made a video explaining that it's a waste of time to worry about device drivers for USB devices that aren't listing at all for any length of time in the Windows Device Manager, Linux dmesg, or Mac system information. I'll link it somewhere appropriate if you want to see that first. In that video, in an on-screen comment, I mentioned that in some cases, a device doesn't even need to work well enough to return a device descriptor in order to list in these utilities. So that you can see that for yourself, I've put together this little demo board. Although somewhat less conventional, I've soldered everything to the copper side of the single-sided board and put that side facing up so you can see everything there is to see. There's nothing to speak of on the back side of this board. As you can see, there's not a lot here. There's a header that a USB cable is going to be attached to, a voltage regulator, a capacitor, a pair of dip switches, and a pair of resistors. That's it. The copper strips are cut underneath the switches and resistors, so those parts aren't being rendered useless by copper running underneath them. Rather than try to solder a USB jack onto the board, I've crimped a 0.1 inch header to an ordinary USB 1.0/2.0 cable. On the outer pins we have ground on the left and USB bus voltage on the right, which is roughly 5 volt. The center two pins on the header are the D+ and D- USB data pins. The regulator is here to step 5 volt down to 3.3 volt because USB data signals are nominally 3.3 volt. There's an output capacitor on the regulator, and I've left space on the input and output sides of the regulator in case I needed more capacitors. As it turns out, they weren't needed. So really, all that's happening on this little board is that the data signals are being individually pulled to 3.3 volt through 1.5 k-ohm resistors if the switch is closed or on. Otherwise, the wire just goes onto a copper trace for a few centimeters and is otherwise disconnected from anything. USB devices are detected when they attempt to electrically connect, not merely because they've been physically inserted or attached. Though most devices do electrically connect the moment they're physically connected, but not everything does. The electronics behind a USB port will pull down on both data lines with 15 k-ohm resistors or something equivalent. Note, when the switches are open on our test board, these pull-downs in the USB port are the only things influencing the data lines. A USB device notifies the computer that it wants to be electrically connected to the USB bus by pulling up one of its data lines to a high level. Naturally, for that to happen, it has to be physically connected. The USB standard says that when you pull one of the data lines high, you're to do it through 1.5 k-ohms. That's why I'm using those values. This 2 in the case code is the number of zeros after the first two digits. So this is a 1 digit and a 5 digit followed by 2 zeros, or 1,500 ohms, that's 1.5 k-ohms. If you do the math on a voltage divider with 15 k-ohm on the bottom and 1.5 k-ohm on the top, you'll see the divided voltage is close enough to 3.3 volts to be considered a logic level high. But you can also just observe that the pull-down is an order of magnitude higher resistance than the pull-up. When nothing is connected, the pull-down is all there is, so it dominates the situation, and the signal is low. When the device pulls up with 1.5 k-ohms, it's pulling up with an order of magnitude higher strength, and so the signal comes to a logic level high. A device pull-up on D- indicates the connection of a low speed or 1.5 megabit device. A device pull-up on D+ indicates connection of something faster than low speed, something at least 12 megabit. So the 12 megabit full speed, 480 megabit high speed, and gigabit super speeds all pull up on the D+ signal to initiate a bus connection. Once the device pulls one of its data lines high, the host computer sends a series of standard USB messages to assign the device a bus address and to identify the device and its capabilities through little chunks of information called descriptors. The speeds higher than 12 megabit are negotiated partly through some combination of extra signaling and USB messages, but there's nothing on this board to do that negotiation. As you can see, there are no integrated circuits on this board apart from the voltage regulator. That is, there are no microcontrollers, no microprocessors, no USB transceivers. There's nothing on this board to fully communicate a USB message. It's just switchable pull-up resistors, nothing that can send a device descriptor, and nothing for a driver to talk to. So let's see what happens in Windows if we enable the pull-up on the D+ signal. So you get the usual USB insertion tone, Windows 10 in my case, followed by an error. In Device Manager, there's now an entry with a diagnostic message attached to it that says, Device Descriptor Request Failed. And that makes sense because there's no electronics here to do any proper USB communication and return a device descriptor. It's just a pull-up. If I turn off the D+ pull-up, you'll see the entry disappears and you'll hear the USB removal tone. Now if I repeat the same process with the D- signal instead, you'll see I get the exact same results. There's our insertion tone, and here's our entry showing USB device, unknown USB device rather, device descriptor request failed. But notice that it does at least show up in Device Manager in a limited way. If you list devices by connection rather than by type, you'll see that the entry moves around depending on where in the USB device tree you've inserted it. So it knows which hub you've attached it to, but not much more than that. There's no hardware IDs or anything like that listed in properties because there's nothing for it to talk to. It's literally just resistors that it's seeing here. In Linux, the dmessage utility is a little more informative, but the story is essentially the same. Here I'm running dmessage with options to wait for new messages and just to show the time delta between messages. Here's what happens if I turn on the D+ pull-up. As you can see, it says I've attached a full-speed device. The system thinks it's a full-speed or 12 megabit USB 1.1 connection because of the pull-up on D+, but also because it was unable to negotiate up to a faster USB 2 or USB 3 speed. That would require a chip to be paying attention to the data signals. You'll see the same failure to get a device descriptor, which makes sense. The dmessage utility is also more explicit about the device not responding to being assigned its USB bus address with the set address USB request. You'll also see the system is trying to power cycle the port in an attempt to get a response. If I try the same test with the D- pull-up, you'll see the same behavior, only it's detected as a low-speed device, since that's what D- pull-up signifies. In neither case will the LSUSB tool show an entry for the device. This is just dmessage. I expect Windows can also provide some of the extra diagnostic information that Linux dmessage does, but that information is not front and center in the Windows Device Manager. So what can you do with this understanding? In short, it can inform your troubleshooting of USB problems. I can't give an exhaustive list of all the implications, but I can give you 4 examples so that you can see how the thinking goes. And then you'll no doubt think of scenarios that I didn't mention. Physical connections. If your device shows up in Windows Device Manager or Linux dmessage in this way, you can be certain that you have connections of some quality between your USB port and your board or microcontroller for data signals. Without those connections, there would be no way for your board or the chip on it to pull the data line up to get the USB attachment process started. Therefore, your cable and the jack that it's connected to are probably fine. In particular, you can be reasonably certain that you haven't found yourself using one of those charge-only USB cables that have no data connections in them. Enable/reset signals. Most chips that handle USB signaling in hardware don't need or have external 1.5K pull-up resistors. Instead, the pull-up is implemented inside the chip. That's true for microcontrollers and USB serial transceiver chips like the FT232, CP2102, CH340, etc. For microcontrollers and USB transceivers, if the chip is in reset, not enabled, or shut down, etc., it will not be trying to electrically connect to the USB bus. So if the chip has internal pull-ups, and it is showing in Windows Device Manager or Linux dmessage with a failure to read device descriptor message, you can at least know that the chip is not being continuously held in reset or otherwise lacking an enable signal. A microcontroller seems to be trying to connect. When microcontrollers initially start up, they generally do so without attempting a USB connection. So if you're using a microcontroller with built-in pull-ups for USB, and it shows up in Windows Device Manager or Linux dmessage with a failure to read the device descriptor, you know that the chip had to have at least run some code to either enable its USB peripheral or at a minimum cause one of its USB data pins to go high. That code could be your code or a USB-aware bootloader. That also gives some indication that the chip is being clocked, because it had to at least run some code. Maybe not at the right frequency, but a wide range of frequencies will allow a microcontroller to run code to signal a USB connection attempt, because that part isn't particularly timing sensitive. Some designs try to connect by default. A Digispark bitbangs USB and pulls its USB data lines to 3.3 volt with an external pull-up. This means that signaling a USB connection attempt is a default behavior for these boards as soon as they are attached. This is true for a number of other boards that use the same or similar circuits on the USB data lines for bitbanging USB. With the chip held in reset for those that have a working reset pin, or with the chip outright removed from the board, the circuit will still pull the USB data signals to 3.3 volt, and because of that will show in Windows Device Manager or Linux dmessage with the failed to read device descriptor message. Under normal circumstances, these boards are running code that will respond to USB requests by the time the host issues them. In order to not list in Device Manager, the chip has to be working well enough to be running code that explicitly drives the data signals low. Anyway, there are too many scenarios to address all of them, but the basic thing is that if the USB data signals are allowed to be pulled high, that's all it takes to show up in Windows Device Manager or Linux dmessage with this message that says it failed to read a device descriptor. I hope you found something in this useful or entertaining.